it's really important that these decentralized systems exist, not just to kind of push forward our own Western societies and bring kind of meaning back into jobs, etc., but also just for power grids and other industry to exist at all.
If we want decentralization to really proliferate, it has to outcompete the incumbent systems. We believe decentralized systems are the greatest way to increase prosperity for the greatest number of people, right? That's why we care so much about this.
It's not the technology itself that drives change.
Creating something beautiful in the world, it's art. You have to be able to design that more decentralized system where it can be profitable. All right. We are live.
We're live.
Inside Going Direct in the deep, dark days of mid-November.
Indeed. Where are you right now, Jordan? You in Paris?
I'm in Paris. Yeah, so nice and gray out. But
lovely.
All right, what are we talking about today?
So today we are talking about biomanufacturing, but we're going to start off with an overview of decentralized production methods, right? So biomanufacturing is one of them, one of the big ones. But we eventually want to get around in future episodes to 3D printing and a few others. Do you want to walk us through and give us like a little overview of what we're going to be talking about over the next few weeks?
Yeah, sure. So before I'm going to bring a little diagram up, and for those that are listening, I can explain what the diagram shows. But we thought it made sense to really dive deeper into the concept of decentralized production and the different, not only enabling technologies that are making this happen, but the different forms of decentralized production, which I don't think many people really realize how many several kind of different ways of producing things are coming together that are inherently more decentralized. And that gets me pretty excited. And as we've discussed at length, if we want to build this going direct economy, the heart of that new system is production. So if you think about kind of the three pillars, production, distribution, and then marketing or direct marketing, it all starts with production because that reorients the rest of the functions. So, all right. So I'm going to share. All right. Here we go. All right. So folks that are just listening, there's a diagram here that's labeled decentralized production. And why we wanted to put this together before we dove deeper into biomanufacturing is this kind of gives a broader view of like what's actually happening from a technological standpoint and why we're so convinced in this move towards more decentralization. And as we've discussed many times before, if we want decentralization to really proliferate, it has to outcompete the incumbent systems. And the reason why we think this is going to happen is there's kind of two kind of horizontal layers that are coming together. The first one, which we call level one in the diagram, is decentralized energy production. So that's a mix of things like micro, modular nuclear reactors, energy storage, decentralized energy storage, and then decentralized grids for distribution of power, and having the production and the distribution of power kind of live adjacent to one another. So there's many different aspects of this which we'll go through in future episodes, but kind of that foundational level is energy and producing it in a much more decentralized way. Obviously, the most common one people are familiar with is solar. So you can take the energy, you can take the light and turn that into energy from the sun and produce power pretty much anywhere with solar panels. And then the second level of kind of horizontal enabling technology that's making this happen is kind of AI, robotics, automation, which we've spoke at length about, and we've done many conversations with roboticists and other folks in the AI space, and we will continue to do so because this level two is what's going to actually allow these different types of decentralized production models to compete with our current ones, which is like the most critical component. And then below the level two kind of horizontal technology, what we listed out here are the four different types of decentralized production that methodologies that are coming together. And so I'll just read through each of them, and then we'll dive deeper into what today's conversation is about, which is biomanufacturing. So first you have 3D printing, or what folks in the industry call additive manufacturing. This is being used pretty heavily in many different industries, especially around specific parts auto parts and parts for aircraft carriers and all types of kind of things that you don't see. But 3D printing is, an interesting one because there's been a lot of hype around it for a long time, more on especially on the consumer level, and it really just hasn't taken off as much as people would have thought. But it is growing and getting very, very interesting, especially because of a lot of the AI assisted design technologies that are coming out to making 3D printing much more efficient. So you have 3D printing, where essentially you can print something anywhere, so it's inherently decentralized. The second is what we refer to as mini mills. And so, what a mini mill means is just think of like a factory today, but think of like just a factory and just utilizing all the newest technologies, especially around robotics and automation, to kind of build, a factory of the future, which is just much more efficient, much more automated. It can be on a much smaller footprint. That's what we refer to as mini mills. And so you might have heard this term, the dark factories over in China that basically operate 24 hours a day, completely automated, making phones and other electronics components. And so, and a lot of stuff going on that's happening in the US, we're seeing a lot new models with people actually calling them mini mills, which is just like a much more scaled down, efficient way to produce something. And then you're producing many more of those facilities in a much more decentralized way where whatever they're making is being consumed. Third is upcycling. So as kind of many folks would have used the term, circular economy of how do you actually use waste and how do you reuse waste and other byproducts as inputs into making new products. And so one of the things I would say on upcycling, I think there's a ton of great companies and projects coming out in there. That one's really, really hard to pull off if you want kind of a market-based solution, which we can discuss why. But it all kind of goes into this theme, though, of how do we go from dirty centralized systems of production to more clean decentralized ones. All right, and then the last one, which we're gonna dig deep into today, but both Reiss and I have spent a fair amount of time in, is biomanufacturing. And so we'll get into it, but just basically at a high level, what that basically means is, you might have heard the term of bio-based chemical ingredient, material, or product. So essentially, it's like using biology to actually make those things. And typically you grow those things inside of bioreactors. So it allows you to actually manufacture whatever it is that we're talking about in any type of climate and any type of location, because it's all done in a controlled setting indoors. And it's all done through a process called fermentation, which for folks that don't know, this is like one of the most oldest forms of especially food production that we have. And this is how beer is made and how bread is made and yogurt. So we'll get deep into that. All right, I'm done off my soapbox. I'll remove the diagram. All right.
Yeah.
You ready, Reiss?
Thank you, Jordan. Yeah, for sure. I think, thanks for running through that. And I think a lot of the terminology in the space is hotly contested. It really depends on who you ask. But we also have different types of biomanufacturing. We have ways of manufacturing even more foods than we already do through crops, through trait engineering crops. So that's something else we can talk about a little later today. Also, just wanted to mention that you put out the energy diagram at the top layer. I think it's really important, and something that's underestimated is how inherently valuable that is to certain societies. You go to Africa, a lot of countries that can only exist using decentralized grids. Their power systems can only exist using decentralized grids. They're not capable of building out a centralized grid system at the moment. Often, a lot of these countries will have too much infighting to enable that, or the infrastructure will be too cost prohibitive. So it would just be a farmer with a solar panel and a battery, and that would be it. Right, so it's really important that these decentralized systems exist, not just to kind of push forward our own kind of Western societies and bring kind of meaning back into jobs, etc., but also just for power grids and other industries to exist at all. So now I've got off that point, let's dive into biomanufacturing, and in fact, let's start with where you left off, which is synthetic biology, manufacturing stuff inside cells or inside bioreactors. So I think let's start with like a little outline of what this looks like. We have essentially cells that we can genetically engineer. We can engineer this molecule that's inside them that codes for all proteins and indeed other small molecules as well in an implicit manner called DNA, right? And if we chop up other bits of DNA from other organisms, we can transplant those into the organism of our choice. So say, for example, we want to produce a protein X, right? Then we would put in gene X into some bacteria and it would pump out lots of protein X. Now, here's a really cool thing. If we want to produce a chemical that's not a protein, we can instead put in something called an enzyme. Now, an enzyme is a protein that can catalyze a chemical reaction and take one product and turn it into another. So let's say we put in enzyme X. So we put in the gene for enzyme X into the cell. That takes a given chemical Y, and then turns that into chemical Z. And then we can output chemical Z. That's it in a really simple manner. And of course, there's lots of other ways you can do it. You can do it in a cell-free way. So you can take the infrastructure inside these cells and put that in a liquid. And so you don't actually have the cells themselves. You just do it within this kind of, within this body of fluid instead. And that's broadly how it works to begin with.
So I'm gonna bring you back to make sure that to help folks that are not as much on the scientifically inclined side as well, which is really important to understand. So no matter the different types of biomanufacturing and synthetic biology, as Reiss was saying, which is inserting certain type of DNA to a cell to create the type of protein that you want. And obviously use the example of enzymes. But what I wanted to just talk about is why this is so important when you think about moving from dirty centralized systems to decentralized clean ones. And basically all of this is done. You need something basically to simplify. You need something to really create that reaction and have something for the cells to feed off of. And it's usually a type of sugar or what's commonly known as a feedstock, versus many of these things, especially chemicals, for instance, right? Their main input is petroleum. So this is a way to actually start making products without using petroleum and oil as the input, which is much better, obviously, for the planet and for health. So Reiss, can you just talk a little bit about feedstocks? It's like the most foundational piece to biomanufacturing.
For sure. So I think if you take a look at the chemical industry, right, it will take a lot of raw chemicals from petroleum. There's a few other raw materials in there as well, but we'll run with that for now, especially hydrocarbons. And as you say, they bring them in, they run it through a very dirty chemical process, often will leach into the surrounding environment, killing trees or poisoning lakes. And then they'll sell the output products that they were aiming for in the first place. We've seen big cases of this, of it kind of going wrong. A great example of this is with PFAS, right? So this is, there's been a lot of cases where PFAS is often dumped into water systems, and that makes people really sick, gives them cancer, etc. It's something well documented about, and there's lots of resources out there to read more about that. But that's just one example of how the chemistry industry is dirty. With biology, what you get is these feedstocks that can be anything organic, anything that's grown. So like you said, commonly it's a sugar, and you go through this process of fermentation where you just chuck in this feedstock. This could be wastes from a crop. So let's say you're harvesting lots of wheat. Usually what you're looking for there is at the top, at the head of the crop. That's what you're using. That's what we use to make our wheat flour, and that's what we eat. But the straw of that is left over. So if we can take that, this leads a little bit into the upcycling that we were talking earlier. If we can take that, dump it into a fluid containing our bacteria that's capable of breaking that down, eating it, and then producing a bunch of enzymes that, can catalyze that into the products that we want at the end. We have something that's much cleaner. We have something that's much more inherently biodegradable. We're not polluting our environment, and we're not polluting our health in the short term.
Great. And so let's talk a little bit about, because when most people hear biomanufacturing or more specifically biotech, there's kind of two aspects to this. We started this conversation in the context of kind of what we what we characterize as industrial biotech.
Sure.
So that's for industrial purposes. But the vast majority of the industry, and why we've had a lot of challenges with the scale up and the cost of industrial biotech, is actually in pharmaceutical related applications. And so it's very important, like for people in the industry, I always talk about it as someone who didn't, like, I've learned a ton over the past 4 or 5 years, but before that, very little on the science side. I just call it pharma and non-pharma. And so can you talk, Reiss, about, most people don't even know how some medicines are made, and the fact that, because this is why the infrastructure is how it is, which we're going to get into some of those topics. But yeah, how biotech plays a role in drug development and production of drugs.
I think what I want to do actually is before we get to that, before we get to kind of the biomed side, I think it would be great to touch a little upon why there's been a big pivot in the industry towards producing pharma products in the first place. Would that be okay with you?
Yes, but that's completely fine. I just think I think a minute or two would be helpful to understand how biomanufacturing is used in pharma related, because I think it brings up the point of what the infrastructure is like and what's holding us back in industrial biotech. But however you want to roll it.
The key thing here is that you need to maintain sterility. Now, you need to do that with biomanufacturing anyway, because a lot of the organisms you're dealing with here are sensitive. These are not involved in some difficult environment where they're competing with lots of different organisms. These are very fragile lab-grown organisms used to sterile conditions. And therefore, if you put any kind of competition in there, the whole batch can be wiped out. And then even worse, when it comes to pharma, it can actually be contaminated, and therefore the batch can't be used for whatever medicine you're trying to produce. But you use the exact same pathway that I described earlier to do that. Of course, you've got alternative ways of using synthetic biology in medicine as well. So you can use things like, you can engineer viruses to deliver gene therapies to somebody who has a genetic disease. And you can modify their chassis so that they can be directed to specific parts of the body and implant that new gene in them. And then you can start expressing proteins that are healthy as opposed to the previous unhealthy proteins that are expressed by that genetic disorder in the first place. And then you've got things like CAR T cell therapy, which is using to combat cancer. That uses this, basically you take white blood cells out. These are your immune cells. You modify them a little bit so that you can heal. You modify them a little bit and then inject them back in the body so that you can target a particular tumor. So those are the different ways in which synthetic biology is used in medicine today, just very briefly.
Great. And so on that point, which is really important for folks to understand, so the vast majority of the industry is built. So when you talk about bioreactors and where you grow the cells and you produce it, and all the infrastructure is made largely for pharmaceuticals, these different drugs. And these different drugs are much lower yield, higher value products. These companies are spending billions, hundreds of millions of dollars sometimes on R&D and developing these programs to have these kind of blockbuster drugs and blockbuster drug releases. So because of all the regulations and how sensitive those cells are, as Reiss was explaining, the infrastructure. So everything is very expensive and made for a high value, low volume product. And then now moving over to industrial biotech, it's just to simplify it, it's the complete opposite, right? So if you're making a chemical or a food ingredient or something, these are much lower value, higher volume products, but the infrastructure that exists has kind of been built over the past 30, 40 years more around pharma. And so on that point, Reiss, I think, and that's something that's holding back the decentralization of industrial biomanufacturing. So I'll let you take it from there.
For sure. The reason why there's that scale problem comes down to two things. Number one is the sterility point, which I mentioned earlier. If you get any kind of unexpected bacteria or microbe in your batch, you have to chuck the whole batch. That could be tens of thousands of liters down the drain. And then you have to clean the whole factory all over again, clean the tank, and then restart production. That can happen at any time. And this is something that's held back the lab-grown meat industry, which I'm sure made headlines about around 2018 to 2021. A lot of folks may have seen that around that time. But, you know, you compare that to, say, a abattoir, right? So where you literally kill animals. The other thing is just the amount of yield you can get from these microbes at all. You know, you're really looking at maximum micrograms per liter. And that's absolute maximum. Usually you're going way less than that, nanograms. When you cascade that over tens of thousands of liters, it really does not add up to much at all. And this is an expensive process. These bioreactors require a lot of power. They've got lots of motors that need to be powered, pumps that need to be powered. They have heat that needs to be provided to the vessel as well. So there's a lot of kind of cost in the power aspects, but then you've also got the labor to just watch it and monitor and intervene in these bioreactors too. And I think it's for that reason that synthetic biology hasn't taken off in, you know, high volume, low value products. And there was a huge attempt to do so, wasn't there, Jordan? You know, we spoke before at a big conference. Well, we've spoken a lot about a big conference that we were both at. We didn't know each other at the time. But we saw many, many attempts. I certainly saw a lot of startups that were working in ag tech, for example, that were trying to produce food products using synthetic biology, and they could only produce tiny, tiny, tiny volumes. And they could never get beyond that fact. And there were some interesting innovations that allowed people to move on beyond that, but we can talk about those in a second. But Jordan, I'm just curious if this resonates with you as well and what you saw at that time from an economic point of view.
Yeah, for sure. I mean, it's like, and I kind of had it's interesting. I have more of an kind of angel investment lens on this because that's what I was really focused on for several years, learning about the space. And what got me so excited about it was the promise of it, right? How it's really enabling the science and the technology. They're enabling technologies to really create more clean, decentralized production. And it just makes sense on many different levels. And I think my takeaway, Reiss, from that time, and I largely stayed away from companies that were making specific products. And what I learned very early on, it was like, we actually need next generation infrastructure. And so I think what I came away was, if you went into a lab of a lot of these companies working on, you know, bio-based chemicals, or maybe it's a food ingredient or whatever over in the lab, and even kind of like cell-based meat, what you realize, you'd walk in there, you would talk to the scientists and you'd be in the lab and you're like, okay, like they might have one or two machines that didn't exist, you know, 20 years ago. But other than that, they were using all the same tools that scientists have been using for a long time. Go ahead.
Can I jump in there as well? Because yeah, that's exactly right. And the problem is they were machines. They were the most complex machines out there that you could buy. I remember one very big company at the time, which I won't mention their name. I remember visiting their lab and they were using the most expensive robotic arms you could buy at the time for manipulating individual test tubes. I mean, can you imagine? You know, these cost like, you know, around $1 million, at least $500,000 each. And it's just crazy capex that was going into that. And only to just move like a little test tube at a time. Absolutely insane. And so these weren't particularly novel machines, right? They were just kind of next step along. They're more like evolutions of existing technology. And that's something that really frustrated me, was that instead of building an alternative to bioreactors, which were inherently cost prohibitive, people would just try to evolve existing solutions. We did see a couple of attempts at trying to move beyond that, very sparse, really on the technological fringe and on the geographic fringe as well. You know, they often didn't take place in the hubs. You know, they weren't happening in Boston, they weren't happening in San Francisco, they weren't happening in these hubs of synthetic biology that we had. They're happening in places like Canada, right? And what they were doing were they were using living organisms as bioreactors themselves. So, for example, there was one company that they were called Future Fields. They were engineering insects to produce proteins, and they would just, these are insects, right? They would just eat trash essentially, right? And then you could essentially kill them and obtain the proteins from them in a much higher concentration than you could before. And certainly a much higher yield, at least, right? Because you've just got a lot more kind of mass there. Anyway, so that was one really cool technology at the time. Another one was using AI to kind of predict genomic edits. You could make now a genome is just the total number of genes in an organism. Yeah, can kind of think about that as the infrastructure for running the organism in the first place, and then the gene that you insert as like the products that you're trying to produce, right? If you can just think about it in those simple terms. Some people would make genomic edits to make the cell a little bit more efficient at whatever product you're trying to produce. And I remember there was one time when I was working with a very small group to pair up these innovations. And that was really exciting because we thought maybe, through these small fringe technologies, we could really bring about that next generation of infrastructure that you mentioned. That didn't happen for a variety of reasons, but that's what really got me excited. And I think if we can keep pushing into those technologies and new technologies that make up that next gen infrastructure, that will really help push the decentralized agenda. Because imagine if you could just, you pop down your local genetic engineer, he modifies some insects for you, and then you put that on a bunch of poop at the back of your garden. It eats all the poop, and then it takes out the protein. And, that's kind of one wider vision that I have.
Yeah, I think there's like endless examples. I think just going back to kind of what prompted your question to me related to the infrastructure. And so I just think it's important for people to know there's a lot that needs to be solved for if we want biomanufacturing to become, and especially in the industrial biomanufacturing side, to become like viable and competitive. And so, when you think about actually creating a bio-based product, you have the actual science, the synthetic biology. So that's actually that's actually like strain engineering and R&D and physically doing experiments. And then you have from there, then you actually have what they call in the industry kind of benchtop, where you put in a very small little bioreactor, a little tank, to do a bunch more experiments. And then you have to start scaling it up, like, from maybe 10 liters to 100 liters to 1,000 to 10,000 to 100,000. So there's a whole scale up process. And so when Reiss and I talk about infrastructure, you actually need next gen infrastructure along the whole value chain. And in addition to that, which is really excited, and many of you might have read or seen the news with what AlphaFold has done, which has been an amazing tool for researchers to visually to be able to see proteins visually and protein folding visually and how they react under different experimentations and editing techniques. And so because of everything coming out with AI and the ability, in simulation to simulate a lot of experimentations and different permutations and combinations of DNA editing to come up with certain behaviors you're looking to do, like, it's a pretty exciting time that's coming together. There is really new, interesting, low-cost lab automation technologies that are being built right now. And I think that serves as the foundation to allow to really help scientists speed up discovery and to create new novel things. Now, that's just the first part. Then you have to solve the second part, which is the scale-up infrastructure. And so, I would just, to kind of finish up on this point, the reality for me is there's bits and pieces of bio-based products and industrial biomanufacturing that's happening and that have been successful. I think that's great. But I just think it's going to be a pretty long arc. I'm talking, maybe 15, 20 years before we start to see the cost really come down, and then more and more bio-based products actually being able to compete in the market. I would put a 15 to 20 year timeline on it. What do you think on timeline?
Oh, timeline.
No, I have no idea. I'm just, but that's just, it just sounded good.
15, 20 years, maybe. I don't know. Right now, I would say honestly, probably closer to 50, but between us, I'm usually the pessimist. So it's somewhere between there. I just feel like the attitude of the industry still hasn't changed. Like working on next generational infrastructure is still very much a fringe thought. People still just want to use existing technologies or evolve them. And that's really just not what we need. I mean, just to go back to that insect example, that solves the sterility problem, period. Right? Now, it doesn't necessarily solve it for things like lab grown meat, sure. But when it comes to producing like molecule products like proteins or enzymes that you can use to produce other products, it solves it, right? You don't need, literally just putting insects on poop, eating them up, and then you're just processing them later on, and you can process them later on under sterile conditions if you have to. But it solves it in terms of the cultivation of the products in the first place. The fact that we're not seeing more people lean into that, I think, is crazy to me, for sure.
Yeah, I mean, I think there's just a lot of pieces that need to be built. But like I said, I think kind of in the world of biomanufacturing, if you kind of always look at the idea is how do all these technologies and any of this stuff kind of come together to make it simpler and bring the cost way down. We saw this with the human genome product, the cost of editing DNA just completely, I don't have the numbers in front of me, but the cost is just completely nosedived. And so that changed the whole industry of being able to actually edit DNA or to take something's genome and edit the DNA.
Just to jump in there, it was more to read the DNA.
Read it. Sorry.
Yeah, read it. No, it is an important differentiation, right? But reading is still super important in terms of being able to edit it, right? So your kind of underlying point is on the money, for sure. I think something else that please go ahead.
No, that's I'm just giving that as an example, right? That kind of led into where we are today, and so we need a similar kind of cost curve decrease on actually on the discovery of new potential like novel molecules, the experimentation, the scale up, like all of it needs to be built if it's going to be economically viable and compete in the marketplace. And yeah, it's going to take a while.
And let's think about what drives that cost curve for reading DNA, right? It wasn't evolving the same old Sanger sequencing that was used at the time. Sanger sequencing, just for context, is a very short read frame. So short amount of DNA you can read at any time. Method of reading it is very slow, very laborious. And eventually we kind of scaled it up until we had things like Oxford nanopores, right? But those two technologies are extraordinarily different when you look under the hood. We haven't seen any of that with scaling. We haven't seen any of that really with discovery, or we're starting to see more of that with discovery. Something else I'd love to see the use of more is directed evolution, right? Which is essentially using evolution itself, but you can do that under cross-organism competitive. Maybe this is getting too technical for this podcast, so I'll leave that for now. There's definitely, if you're curious, it's definitely worth looking into directed evolution as another potential solution to solving.
Okay, so I'm gonna shift topics here. So I know something you wanted to talk about, which is, we kind of covered where we believe, just high level, kind of what needs to happen on the infrastructure side to actually make biomanufacturing on the industrial side kind of competitive in reality. And one of the areas that you mentioned to me, I know very little about, so I'll pass it over to you, is kind of trait modified crops.
Sure.
And just so I want to make sure we're clear. When you say trait modified crops, are you just referring to GMO or genetically modified or organisms? Same thing?
Sure. Like if I'm going to shoot straight, it's going to be GMOs. But yeah, essentially trait modified crops are GMOs. There's different, but I mean, there's how can I put this? GMOs usually refers to like one particular way of modifying a trait. Now a trait is a particular characteristic of a crop or some organism. For example, if it's something that's very tolerant to salty soils, that is a characteristic, right? That is a trait. GMO, or genetically modified organisms, has usually been edited in a particular way. There are alternative methods of editing that mean that you don't need the GMO label, but that's just a technicality. Let's kind of take a step back for a second and think about the decentralized context here. When we want something decentralized, we want something that's when we say something's decentralized, the way that we get to that decentralized means method of production is by, especially in the West, is by lowering costs and also extending the capability through technological means that allows us to manufacture X thing in that region. Would you agree with that, Jordan?
Yeah.
So
yes,
one of the issues, especially with climate change, is that we're seeing the variety of crops you can grow in a given region reduce over time. So, take for example, portions of South America are now unable to grow coffee that historically have been growing coffee for hundreds, if not thousands of years, right? The entire areas of Spain now, which, to be honest, are just not suitable for growing tomatoes. And, if you're in the UK, a lot of your tomatoes are going to be imported from Spain, which is a worrying thought for a nation that depends a lot on imports for food production. The question is, how can we bring back more of that food production into a local region? Well, so the question is, how can we bring more of that food production to a local region? Well, the answer is through decentralization, and one of the methods that we do that is by expanding the set of traits or improving the set of traits for a given crop. So I'll give you an example. Say you want to grow coffee in a given country, but the country is way too hot. You can't grow coffee there. So you have to depend on some other country to import it from. What if you could modify an existing coffee strain so that it was more heat tolerant? So you could grow it in that country. But all of a sudden, you don't need to rely on that centralized producer anymore, that centralized producing country. You can bring it into your own country. Modifying crops to improve a particular characteristic so that you can grow it in an improved way, or so that you can actually expand the regions where it can be improved, expand the regions where it can be grown in the first place.
Great. I wanted to just jump in here just for the folks that are listening, because it's interesting that you brought up coffee. And so actually a couple of weeks ago, we released an episode with Alan Perlstein, who's the founder and CEO of California Cultured. And so they're actually doing cell-based chocolate and coffee. So they're actually utilizing biomanufacturing in bioreactors, not trait modified crops, but another approach to where they're actually using cocoa beans and recreating cocoa through plant-based cell culture and out in California, and doing that through kind of industrial biomanufacturing method. And I just wanted to bring that up as just to give you an example. These are multiple ways the kind of broader theme of biotech can be utilized to decentralize production. So it's not just it's not just one specific thing. So I wanted to bring that up.
Yeah, and actually, plant-based cell culture is definitely a less utilized technology. Was there anything that jumped out at you during that interview? Any big takeaways?
Well, and in full disclosure, I was a very early investor, and it was I think it's the only company in the space, product-based company in the space that I invested in. Partly because I just love chocolate, and the more
hang on, that's a revelation to me. What's your favorite chocolate?
What do you mean? Like the same brand?
Brand, whatever.
Oh, I don't have like a favorite brand. but I'm a pure dark chocolate guy. 80% plus. Yeah.
Wait, how did I not know this? I'm literally the same.
I have no idea. So before, my wife is French, and so you over in France, it's like much more part of the culture where like everyone has a little chocolate with their coffee or at the end of the meal. And so she got me into dark chocolate. I'm a fiend for it. It's my main sweet tooth fix. So
amazing. But anyway, you were telling us about some of these takeaways.
Yeah. So I think, so I've followed their story. I mean, I think the most interesting takeaways for me, it's more actually for like how, if you basically say we're going to, in this case, completely remove the farm from the process, in the sense of, obviously there's big problems with deforestation, the child labor. There's a big issue with cocoa supply now and where it can even be grown. And so the areas that we spent a lot of time was also on the commercial strategy, like how do you actually sell these ingredients and get them into products and into the market, but more on the science and production side. I would say one of the things, because we started the episode that was really interesting, Reiss, around how, like, just how chocolate is made, like chocolate 101, right? And cocoa production. And he said a couple really interesting things to me, which was one, he goes, for sure, most warehouses that, that warehouse the cocoa is they're largely depleted. So they're working on very low inventory levels. And what's interesting, there has been a bunch of reports that have come out recently that there's certain products, like big chocolate companies now, the products, especially in the US, that they sell, they can't even claim, like the chocolate content is so much lower now that sometimes they can't even claim a certain type of product now because of the availability. Yeah, I forget. I don't want to mess this up. I'd have to find the headline. Maybe when and the next, while you're doing when I pass it back over to you, I'll look it up and get it exactly.
Okay.
But the point that he said, which was very fascinating, he basically said after the cocoa is grown and then taken off the tree and then dried and then it goes through its process. He basically said once it's like dried and in like the warehouse, before it ends up in a product and like in someone's hands is like over a year, which I thought was like very interesting. I didn't fact check that, but I thought it was very interesting when you think about, man, if we know we just need alternative solutions for production of cocoa. That's just obvious if you look at the numbers, like we do, and the increased amount of demand. So this whole idea is like, man, well, if you can actually figure this out, and they have some very novel approaches, and they're a very crafty team around. They've designed their own bioreactors, and they've done some really interesting stuff on the production side. But I just found it fascinating how inefficient it was, and if you can figure this out, is just one alternative factor for making cocoa and chocolate, and you can bypass that whole kind of globalized supply chain, multiple steps in the process. Pretty interesting.
And it brings back, well, it doesn't bring back, it actually enables for the first time production of cocoa in regions that couldn't traditionally produce it.
That is exactly right. So that's what's the most interesting thing to me about biomanufacturing is that. And I think there's certain product categories and areas where it's way more interesting than others. I think chocolate and coffee are two of the most interesting because of the dynamics and how it currently works.
And I've got a question for you, actually, just from like an economic point of view. Typically in economics, we see these scaling laws, right? Like the larger you increase scale, then the cheaper your product is per unit, right? But does that really apply to biomanufacturing in the same way? Because because of the sterility problem that I mentioned earlier, you can lose masses of batches that can quickly eliminate any kind of scaling efficiencies you get. So I'm curious, actually, if you're better off producing smaller volumes, maybe like tens of liters at a time in a local region, and then that basically being less cost prohibitive than scaling up to tens of thousands.
So there's the short answer is yes, the scaling laws apply just like anything else. And the reality is if you want to be cost competitive, you need substantial volume, whatever it is that you're making, because your margin, your cost to make an additional kilo or whatever or pound of what you're making is dramatically going to decrease as you scale up your production, because you can spread your capex and your facility costs across, right? What you're getting at, which is very real, Reiss, and which is where the issues are, and this is why a lot of folks in certain categories, especially kind of a lot of the cell-based meats and the piece where sterility is like mission critical. They believe that because the cells operate and can get contaminated so easily, instead of having those very large reactors, it makes sense to have many more smaller modular bioreactors, which is what your question is. And so there's two main cost centers when you talk about the scale up. I mean, beyond the actual equipment, of course, but the first is yield, right? So actually when you're growing that protein and you're growing those cells in that protein, and the question is like, how fast does it proliferate? And so, and then not only fast, but then there's this whole, I don't get too technical here, but downstream processing process. which is, filtering out the input that you want, and like that whole purification process, that's usually one of the most expensive parts. So unless you have a novel approach on the purification, the downstream processing, it just decreases the benefits of just the economies of scale of just going larger. So
yeah, actually, that's a great point. And it really depends on the product as well. If you're just producing proteins, then you're going to have a slightly easier time. But if your like end product is like a fat, like a lipid, you basically have to pump, you have to pump your fluid, your product, through during that purification process through these columns that get clogged up by a bunch of fats anyway.
Yeah.
And that means that you have to replace them. You have to buy new columns every single time. It's like buying new infrastructure after a few goes. It's crazy. So yeah, totally get that.
Well, I think to your point, Reiss, I think this is what I think you were getting at earlier in the episode. And if I distill it down, what you were talking about, the industry has to stop looking inward for solutions, and you have to look outwards. And it was funny, I just felt it right away. Like the folks that I were typically drawn to building in the space and looking to build solutions had much more of this kind of DIY kind of biohacking mentality. It was like a community that I really connected with how they were thinking about it. And to your point, Reiss, like these things that you don't think about, it's like, okay, what you actually need is a really low cost way for like a self-washing mechanism or a self-sterility mechanism for the column to actually wash itself out, right? And like you need these things throughout the process that, like, if you look at how it's done today, where you're buying really expensive liners, because that's what most pharma companies do. They'll buy like a liner and then just throw the liner out every time they do a batch. You need to be thinking about those creative kind of very DIY things to affect those cost centers. I just want to make sure I brought that out because it's a very important point.
You need to get scrappy.
Yeah, totally.
You need to get scrappy and you need to think outside the box. And I think the problem with biotech today is that it is still heavily, heavily dominated by academics. A lot of the startup companies you see are just spin outs by labs. And those academics will just continue to do the traditional thing most of the time. Not always, but most of the time. And to your point, it's the DIYers, the kind of renegades who are changing things up.
You bring up a really good point, because it was very interesting. It took me a while to be, like, I almost was self-conscious about this, because I remember sitting when I first started getting my synthetic biology 101 class, essentially. Shout out to Jake Wintermute, who was nice enough to educate me.
Were these little one-on-one tutor sessions, or was this like a class?
Well, how I got into it was I started spending more time over in Europe, and then I just like found this Syn Bio 101 class made by this professor, Jake. And Jake was an American guy teaching at what was called before, it was like this cross-disciplinary university in Paris called the CRE. And he was a synthetic biology teacher, but he's an American. And so I just reached out to him. And I was like, hey, I'm like really interested in this space. I'm an active angel investor. I'm in Paris. I'm American. And he's like, yeah, come on by. And so we just like, and he was like so nice. I went into a couple of his classes. We went into the lab together. He was kind of giving me the rundown and how everything works. And yeah. my point of what I'm saying is, between that and talking to bioprocess engineers, man, I was like, the last science class I took, I was 11 or 12 years old, and so it's this space that if you don't I had to do a lot of just basic foundational knowledge. What is a protein? How do proteins work? What is an enzyme? How does, what does the sugar do to make it grow? And like, or the carbohydrate and all this other stuff, and it's a very, like you said, it's really, what's the right word? It's scientists speak a different language.
It's very ivory tower.
Yes.
It's very ivory tower, and it does a great job of using words as essentially a shield. I remember, I think it was Jordan Belfort said something similar of investment bankers in Wolf of Wall Street, in the book. He says, investment bankers are great at keeping other people who don't know shit about investment banking out by just using complex words. It's the same thing as synthetic biology. And actually, the principles, like what's so important is understanding the principles behind things. It doesn't, the labels and the name doesn't really matter at the end of the day. I think Steve Wozniak talks about this a lot, about electronics as well. So, yeah. Yeah, I agree.
I'm looking up, just real quick, sorry, I'm looking up the
chocolate
piece
statistic?
about the chocolate products, and I gotta try and find it.
Curious. I gotta listen to the full episode, honestly. Yeah, chocolate's one of my favorite things. Shout out to Cadbury's, just saying. I don't know if you have to cut that out now, but I love Cadbury's. Have done since I was a kid.
Wow, Cadbury eggs. Well, that's something that Britain's given to the world, right?
Yeah, exactly. And Quakers. Let's go. Yeah. I'll give you a sec to bring it up.
I can't find it. I gotta find it.
We can put it in the show notes.
I know. I'll try and find it. But it was a thing about like the people noticing like a big difference in taste of the candy because just like the volume of chocolate is lower or something. And it was a whole report on it. And I can't find it right now. But anyways. All right, so let's move towards wrapping up maybe here in a couple minutes. What's anything else you wanted to mention? Any topic? Yeah, on the trait modified crops.
For sure. So I think a lot of the technologies we've spoken about that which are either trait modified crops or using plant cellular culture. These two things are great and all, but they still require a lot of land, especially obviously farming crops, right? I suppose plant cell cultures don't require too much land. There's an alternative to plant cell culture as well, though, that still uses crops, but doesn't require a lot of land. And that is making crops so salt tolerant that you can grow them on rafts in the ocean. Now, this is great for small island nations, and it's also great for nations that have kind of a high amount of coastline, like the UK or Norway and Chile, these kinds of countries, where you can put these rafters, maybe it's filled up with a bunch of nutrients, and then you float it on top of some water, and typically the crops will just die because it's way too salty. But if you can make them salt tolerant enough that they can actually use them in a similar way that we grow plants on hydroponic systems, then that's a great way of spreading the accessibility of certain crops and the ability to grow crops at all to portions of the world that can't usually do that.
So on that note, let me ask you this question. So I'm gonna kind of wrap it back to everything that we talk about at Going Direct, and one of the main kind of phrases we have is what brought us together is we believe decentralized systems are the greatest way to increase prosperity for the greatest number of people, right? That's why we care so much about this. And we've discussed a lot about what's holding just broadly the biomanufacturing industry back. And basically, if you could wave a magic wand, or the most important, if you were to pick one problem to solve right now to move the field forward, across all the different topics, whether it's industrial, biotech, trade editing crops, anything, any application of it, what would you want solved? What part of the stack would you want solved that you would think would result in the most amount of progress to get more commercially viable products to market utilizing these production methodologies?
In a decentralized way?
Mm-hmm.
That's a great question. Oh my God, can I pick two?
Sure.
Okay. I think I want to see a bridge between kind of R&D and scale. I want to see that bridge close from years to months. I think ways that's possible is using things like cloud labs. This is something a few of my friends are working on, where you have these labs, cornered wherever they are, and you just access them through your laptop, right? And you just say, I'm going to submit this I want to execute this experiment today, and it'll execute that experiment, and then it'll give you results, and then you can keep doing the R&D remotely until you've got, a result you're happy with, and you can take that away and put it into production. I think that's something I'd like to see more of. So yeah, cloud-based labs to collapse the R&D time and also make R&D way more accessible to your everyday person. And the second thing is I would just try and solve the sterility problem even further. I think the insect living bioreactor method is a really interesting one, but maybe there's other better methods out there that I'm not aware of or haven't thought of. But if we can find a way to just completely avoid the sterility issue, or at least reduce the cost or the potential loss through contamination, that would be awesome. And I think that makes production itself a lot more accessible to a local area who might not have the best equipment.
Cool. I'll give you one and before we wrap up. So, to kind of the automation, the cloud labs is a big one for kind of apps like speeding up the R&D. The design was it design build test cycle, however you call it in the lab. But I heard a speech at a materials conference a couple of years ago, and this is all bio-based materials conference, and one of kind of the CEOs, founders of one of the leading companies in the space, they're making some sort of like mushroom-based material. I don't remember. I forgot what company it was. And he said something which really resonated with me, and I think this is what I would want changed, which is the beauty of synthetic biology and kind of this idea of designing and editing cells to express themselves in unique, novel ways. I think largely the industry has sold themselves short, and scientists are selling themselves short with trying to emulate what we already have in the physical world. So I'll give you an example. It's like the whole move in the material space was like, let's create this like mushroom-based leather. Everything was called leather. So no. Why don't you just invent your own material that has this own properties that you can only get by doing this type of work with synthetic biology? So basically what that means for me, it's like, I would love to see between, computational biology and with all the biology focused AI, LLMs coming out and people working on that, I would love to just be able to get a much more rapid discovery of new novel ways to edit cells and to that express them in really novel ways as proteins. I think that's what I'm looking for, because I think that's what the promise is versus trying to emulate what we already have in today's world.
Yeah. And that's what creates a more successful company, right? And I think we definitely saw at the time when synthetic biology was at its peak, the more successful ones were the ones who were developing brand new materials.
Well, I mean, it's also like just reality. It's like, okay, you're going to do all this work to like try to emulate leather. I mean, leather is pretty fucking awesome. Like, let's take away the animal piece and the sustainability piece. But in general, I would, the reality is if you get like a nice leather belt or shoes, or if it's a nice high quality product, that lasts for a very long time. Like really long time, So anyways, all right, my man. Well, thanks for walking us through the more scientific technical stuff, because I'm definitely not well-versed on that at all. And yeah, man, enjoy the day, and look forward to speaking next week.
No, thank you as well. I always get a little nervous on these after we haven't done one for a while, so I felt like I tripped over myself a little there, but I'm glad that I still came across well. And thank you for your insights as well on the economic side. We didn't really get a chance to dive into biomedical tech today. Maybe we can do that for a future episode, but I think we want to do a couple of deep dives next time on 3D printing to begin with, going back to that decentralized production methodology stack that we spoke of. So yeah, if you want to listen to that, stay tuned, subscribe, and we'll see you next time.
Yeah, and just one last little show notes as one last message. So basically, we're putting monthly recaps out on Substack. So subscribe to us on Substack. That's really where we're going to be putting a lot of our energy and kind of building the community of folks out that really believe in this kind of going direct economy. And these conversations specifically will be released on a weekly basis across YouTube, Spotify, Apple Podcasts. But kind of the writing and really where the connections is going to be is on the Substack community. So come find us at Going Direct at Substack, and we'll put the show notes as well.
Yeah, and if you want to talk to Jordan or I directly, that's a great place to do it as well. We have a chat, don't we?
Yep, exactly. Just reach out to us directly through Substack, and look forward to hearing from you. All right, man. Gotta hop.
Bye.